Okay. Well, welcome everybody to this session of the AMCA and Odell Fan Education Series. I wanted to just reach out. My name's Nathan Martin from Odell. Most of you are familiar with me. I'm president of Odell Associates. I'd watched some AMCA presentations in the past, and they've always been very educational and informative. Reached out to Lisa from AMCA to set up some internal training, and while we were in the midst of setting up that training, realized that this would be a really good series to put out to our engineering community as well. So Lisa was good enough to work with us on coming up with a series of presentations that will happen over the next 2 to 3 months, speaking anything from fan laws to fan calculations, fan maintenance, system effects, duct systems. So it should prove to be very informative for everybody. Lisa will speak here shortly, just talking about the requirements for this new platform we're working with. But I did want to introduce Bill Howarth from Ventilation and Fan Consulting Services. I'm excited to hear what his presentation on fan laws. So thanks again, everybody. And Lisa, I'll let you kind of take it away. Thank you.
Great, Nathan. Thank you. Welcome, everybody. I am Lisa Cherney, the Education Manager for AMCA International. I am going to share my screen here with you all. Yes, our presentation today is on fan laws, an introduction to their application. And this is me. I've been with AMCA since February of 2019. I work on educational programs. I am the liaison for AMCA's Education and Training Committee. I have a variety of responsibilities, webinars, online learning, etc. So a couple of housekeeping notes for these presentations. The audience is muted for the session. If you have questions for Bill, our presenter for today, you can submit those via the platform. On the right-hand side of your screen, there should be at the top of the screen a couple of options, a chat option, a Q&A option, etc. And I do want to let you all know that if you do type anything into the chat or the Q&A in this mode that we're in right now, it is visible to everybody on the platform. So that's just a gentle reminder that what you put there can be viewed by the entire audience. The session is being recorded. The recording will be available on the Odell website within 48 hours of today's presentation. For anybody that is interested in earning PDH credit for the presentation today, please know that you do need to stay with us for the entire program. And then there will be a follow-up survey that will be emailed to everybody in a thank you for attending email about 1 hour after we conclude. For people seeking PDH credit, you do need to complete that survey to qualify for the credit hour. But of course, we would love everybody to complete the survey so that we can get your feedback on how you feel about these sessions and presentations. So again, for Q&A, you would go to the interactive panel on the right side of your screen, select Q&A, which is an option at the top, and type your question in. You can do that at any time during this presentation, and we will get to those live at the end of the program. I do need to mention that the PDH credits that we are issuing are the result of our membership with the Registered Continuing Education Program. RCEP does not endorse or deem any approval for the content of today's presentation. And a quick disclaimer that the information contained in today's session is provided by AMCA as an educational service only. It is not intended to serve as professional engineering or manufacturing advice, and the views and opinions expressed in this activity are those of the presenter, and they do not necessarily represent the views of AMCA International. We are not endorsing, sponsoring, or recommending any particular company, product, or application through presenting this information, and under no circumstances, including negligence, shall AMCA be liable for any damages arising out of any party's reliance upon or use of the content contained in today's program. And all of our programs, obviously, are copyrighted, so any reproduction, distribution, display, or use of the materials without written permission is prohibited. And so, with all of the boring content out of the way, let's get to the reason why we are all here. I would like to introduce to you Bill Howarth. He is a consultant to AMCA International, and he is also the president of Ventilation and Fan Consulting Service International. He has been a consultant to AMCA. Bill, you can correct me if I'm wrong when you join us. It says 2017. I think you've probably been a consultant to us for much longer than that. Bill does have 30 years of experience in fan engineering and sales at Illinois Blower and Hartzell Fan. He is a current and past instructor for the North Carolina Industrial Ventilation Conference. He's been a member of the U.S. delegation for ISO Technical Committee 117 on fans, and he's an active ASHRAE member and is a wealth of knowledge on the topic that we are about to approach. So, Bill, I'm going to stop sharing my screen and turn it over to you.
Good morning. Okay. Good morning. Can you see that?
Yes, sir.
Okay. Thanks, Lisa, and thanks, Nathan, and thanks to Odell and all of you that are joining us this morning. As Lisa said, I have a lot of experience with fans and have been doing the fan laws just about as long as I can remember. So I hope to provide some of my knowledge to you guys so you'll have a better understanding of how they're used in the fan industry. I have in my presentation notes insert fan humor here, and I actually had a joke about the devil and a clock and a lawyer, and they use it as a fan, but it's a little bit too long. So we're going to move on now and actually go into presentation mode. And I'm going to switch to the laser pointer here. So the purpose of the learning objectives for today's presentation are to define what a fan rating is, understand how fans are tested and their associated variables, recognize a fan curve, recognize the fan laws, and understand how the fan laws are used in the development of fan ratings. So the various topics we're going to go through in order are fan ratings and testings, the variables in fan testing, introduction to the fan laws, development of a fan curve, and application of the fan laws for developing fan ratings. So we should begin first with exactly what is a fan. And the definition of a fan is a device that uses power, a power-driven rotating impeller to move air or gas. And AMCA is the Air Movement and Control Association you're probably all familiar with. AMCA is the worldwide recognized expert in air movement and related measurement. They're an independent organization of manufacturers that develops uniform standards for testing and rating air movement related products from fans, dampers, louvers, flow measuring stations, and associated products used throughout commercial and industrial environments. Here we have copies of the AMCA seals. AMCA has over 300 companies, just companies, with certified rating air performance. Each one of those companies might have 1 to 20 or 30 catalogs, and each one of those catalogs might have from a few models to 30 or 40 models in a single catalog, and each model might have hundreds and hundreds of ratings. That all adds up to thousands of ratings for air performance products. AMCA confirm everything that's certified. AMCA has confirmed that the fan ratings are calculated in accordance with the fan laws. So a fan performance rating is the pressure rise, total or static, and the volume of airflow generated by a fan, its power consumption at a given density and a given speed for a given point of operation. So here we have a fan curve. A fan curve contains a lot of information and is very often confusing to people who don't look at them all the time. And most people in the fan industry, unless you're in the applications department or fan engineering, don't see fan curves a lot. They just see numbers on a page. So what that number on a page represents is this area right here, where the fan is actually going to operate. We have a system curve here, which represents the resistance in the system, and flow versus pressure curves here, which represent the airflow in CFM and a pressure that the fan is going to develop in inches of water, typically. In the U.S., it's almost always CFM. In my experience in Canada, it's cubic meters per hour or CFM in inches of water or millimeters of water. Power is displayed in horsepower. And for this particular fan, we have a resistance curve that's going up through 15,000 CFM, and it's intersecting the total pressure curve, which is the higher curve here, at 6 inches of water, as represented by this line going horizontally. This is our flow of interest. And so if we continue on up, we have a flow versus power curve, this brown curve here. And we're intersecting the point here, and we go across, and we're just under 20 horsepower for the point of operation for the power. Other things on this fan curve are the size of the fan, and the size is typically somewhere close to the diameter. And this fan in particular is a 33-inch diameter. This is the RPM 1205 that this fan would operate. And this is looking at a density, which is the air density of 0.75 pounds per cubic foot. And we also have the outlet area, which is used for calculating the velocity, pressure, and a few other things. We also have a little bit of information on how the fan was tested and how the FEI, which is the fan energy index, there'll be a whole separate session on fan energy index, how that is calculated. And what it was included in the fan performance rating. The power ratings here don't include transmission losses. So if you have a belt drive, that would be a little bit of an additional loss on the fan. So how is that fan curve produced? Well, that fan curve is produced by an aerodynamic test. How much air and pressure the fan delivers is going to be established by a test. And this is a picture of a fan in test at the AMCA laboratory in Arlington Heights. The fan here is tested with an open inlet. You can see the inlet of the fan right here, and a ducted outlet into the test chamber. The AMCA lab is an A2A accredited lab and is recognized by the National Institutes of Standards and Technology. The fan performance is typically tested to ANSI or AMCA standard 210, which is laboratory methods of testing fans for certified aerodynamic performance ratings. If you test a fan to AMCA 210 in a certified lab, you can send that same fan to another certified lab, and they are going to get the same results within about 2%. AMCA operates a lab certification program where they actually send test fans out to labs so that they can check the calibration of their the laboratory and make sure everybody is getting the same results. ISO 5801 is another fan testing standard, which is very similar and in technical harmony with AMCA 210. So I mentioned the AMCA 210 laboratory methods. Inside there, here we have another picture of a fan with a smaller chamber, but it's still an AMCA flow test chamber. In the AMCA standard, they have a series of different figures you can set up for your fan testing. This particular figure is a figure 12. And when you look at it in the test standard, you see this sketch right here. Here's the actual fan that's on test, and you have an optional inlet and an optional discharge duct, and then it goes through the chamber and you measure pressures and temperatures at various points. Inside there is a nozzle wall, and here we have a section view of what this chamber right here looks like. So the fan discharges into the main chamber. Inside there is a settling means, and the settling means gives a nice smooth laminar airflow across these flow nozzles. These flow nozzles are similar to inlet cones. They have a defined shape. And when you measure the pressure drop across a nozzle wall, and you are within the parameters for the velocity across the wall and things like that, then you can actually calculate the flow directly. Then there's another settling means on the side, on the discharge side of those nozzles, and then an exit out of the chamber. On this particular chamber, there is a discharge damper so that they can regulate the flow and test at various points to determine the fan performance. So during that test, we're going to measure the flow indirectly, as I said, across that nozzle wall. You could also measure the flow in a duct with a pitot tube, which measures velocity pressure. Or you could have a flow measurement station of some sort. We're going to measure the fan pressure at various points. On the inlet pressure, on the fans that we just saw, the inlet pressure is 0. There's no inlet duct to have a negative inlet pressure. We're also going to measure how much pressure the fan is developing. We're going to measure the fan power. We can measure that a couple ways. We can have a calibrated motor, which in this instance here, we would measure the watts going into this motor, and we would have a calibration curve so we could see exactly how much horsepower it's putting out at a given speed and current draw and voltage. We could also measure the power with a rotating torque meter. We're going to measure the speed with a tachometer or a strobe, something like that. And then we're going to measure the air parameters, a dry bulb temperature, a wet bulb temperature, the barometric pressure at the site, and the system temperatures. So as we said, to get accurate prediction of aerodynamic performance, we have to measure the flow, we have to measure the pressure, we have to measure the power, speed, and the air parameters. We're going to measure that at various points on the fan curve. We saw that discharge duct, and here we have a discharge duct represented as a blocking of the outlet of the fan. That discharge duct is actually mounted on the discharge of our flow measuring device. So here we're wide open on that fan, and we measure at this point, we measure the flow, we measure the power that it's producing right here, and we measure the speed and the other air parameters. We do that at various locations, and in this curve, there was actually a point taken here, 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 and at each point where you see a little change in the shape of the curve, there's probably a test point at that location. So a typical test will take about 10 readings, and to get these readings out here at free delivery, they will actually install on the discharge side of the chamber and a supplemental fan, an auxiliary fan, to reduce the pressure at the discharge of the fan to 0, so we can see what free delivery looks like for the fan. So the test data is collected per the standard, and then the values for these different parameters are calculated per well-established formulas. We're not making these formulas up each time a fan is tested. These have been used with very minor revisions over the years. Same formulas. So that we measured the differential pressure across our nozzle wall, and that gives us a flow. We measured the power going in. We have the static pressure that the fan is developing, the speed that it was taken at, and we calculate what the air density was. So those are our variables, our flow, pressure, speed, density, and the size of the fan. And you'll notice here that the results are at slightly different speeds. This is all the way at 1506 RPM, and our low is 1499. The density during the test also varied a little bit. A typical fan test takes about an hour to perform, maybe a little bit less in the AMCA lab because they are fully automated there. But your density can vary a little bit. It also varies because of the temperature in the room changes a little bit as you're doing the test. So now we're going to want to normalize this fan data. So now we have to talk about something called standard air. Standard air is air that's at standard density, and it's the reference gas for fan catalogs, for fan performance test results, for rating tables that you see within catalogs, and for data sets for catalogs. You might hear it referred to as STP, standard temperature and pressure. In nature, standard air is very rare. You have to be at sea level conditions, and your barometric pressure has to be at 29.921 inches of mercury, and you have to be at 70 degrees with dry air. So it's hard to get actual standard air in nature. In the Chicago area, I know that whenever we do a fan test, the air density is pretty close to about 0.0725 all the time. So there are some things that will change the fan conditions. And when you change the recipe for the air, you change the density, and you change a factor that is used in calculating that density. The factors are temperature, pressure, and ingredient gas mix. Typically, we're just using straight air, which is mostly nitrogen and oxygen. So we don't have to worry too much about the ingredient air mix unless you're going into a refinery process or something like that. So you have temperature, pressure, and the gas molecular weight. Any one of those changes, it changes what the density is of the air that you're using, and you want to come back to standard air for converting this fan curve. So the fan laws are used to calculate fan performance at other speeds, at other air densities, and at other fan sizes. And when I say other sizes, I mean where impellers and casings have the same dimensions. The blade types are the same. The only thing that is different about the fans is they are larger in diameter, and they are otherwise proportional. The fan laws are like the pump affinity laws. Maybe you've heard of the affinity laws. The fan laws apply where Reynolds numbers are similar. So that applies to speed, density, and size. Typically, fan performance, fan Reynolds numbers are very similar. So here we have our first basic fan laws. They're used to normalize the data that we collected before to standard conditions. So we're going to use an average RPM. We're actually going to go a little bit low on the RPM to 1500 because it's a nice round number. And we need to standardize that to a standard air density of 0.075 pounds per cubic foot. So the first fan law covers flow, CFM. Your CFM for your new point is going to be proportional to the CFM of the old point times directly proportional to the RPM and the compressibility factor. The pressure varies a little bit differently. The pressure is for the new point is proportional to the pressure from your original point based on the ratio of the RPM change squared and the change in density. So a lot of those points were at about 0.0724 pounds per cubic foot density. And now we're going to be going to this value of 0.075 pounds per cubic foot. And once again, we have that same compressibility ratio in there. The power is proportional down here to the first power we tested at times the cube of the ratio of the new speed to the old speed. So we're going maybe 1505 was our original, and 1500 is our target speed. So that's going to be cubed. That's going to affect our power. And then the density is going to also impact the power, but that's a proportional relationship. And then compressibility is going to also affect that relationship. What compressibility is as you pressurize the air, that's going to impact the volume of air, and then the volume is going to be reduced, and so the density is going to go up, and so how much energy, how much power you put into the air is going to affect the temperature. So all those things go together and impact the results of our flow and pressure. And I'm going to show you here, this is the calculation of compressibility. As I mentioned, the volume changes with pressure and temperature and power. The pressure changes with volume, temperature, and power. And the power changes with pressure, volume, and temperature. So that all those go together to change your flow and pressure and density. That's an iterative process. You have to go through this process about 5 times before those numbers for the compressibility coefficient converges. So in this presentation, we're going to assume that compressibility is equal to 1. Our compressibility ratio will be 1. And typically for fans below 10 inches, it is very, very close to 1 and can be neglected. So here's our first point. We took a point in the middle of the curve where we measured a flow at 16,821 CFM, a static pressure of 12.3 inches, and that was at a density of 0.0724. So we're going to adjust our pressure point. And so here is our raw data pressure point. And when we go through the fan law calculations of our original CFM at 16,000, and we go through our RPM change from 1499 to 1500 and our density change, that value converts to a slightly higher value for pressure. The flow changes just a little bit. Our big change here is due to the density change. So our flow doesn't change much, but our pressure that we're seeing here goes and changes. Down here at the bottom of the screen, I have all 3 of the formulas just for your reference as we go through these slides. So I'm going to back it up just now. If you watch these points here, these are the pressure points, and the pressure point is red, the flow along the bottom, and the pressure along the left axis. So that's for the flow and pressure points. Now we're going, if you watch these data points, we're going to go to the power point, and you saw them jump up. That's because they are read along, they are horsepower values, and they're read along the right axis for the horsepower. The values for our horsepower originally was 41 at a flow of 17,000 approximately. And our new point at a standard air density of 0.075 pounds per cubic foot for standard air, and our speed that we decided to normalize to of 1,500, our point jumps from 41 horsepower to 43 horsepower. It jumps up a little bit more here. You can see a little bit larger spacing between those points. So the next thing we see here, we have gone through and done the same thing for every point on that fan curve, from our original raw data here to our standardized data here. All these points moved up slightly and just a little bit to the left. So watch the data points when we go to the next slide. We took away the raw data and we curve fit through the normalized data. This is all for that same fan, and it's normalized for the 36.5-inch diameter fan at 1,500 RPM at 0.075 pounds per cubic foot. So this is a curve fit, and the curve fit is just a standard least squares method of curve fitting through 4 points typically. So each set of data, these curve fit points are based on these 2 points and these 2 points. And that goes throughout the whole fan curve. That's why sometimes you can see where the data points are by a little bit of a discontinuity in between where the data point is located. So as I said, the fan laws are used to generate a performance curve at a new operating point. So if we wanted to calculate, I'm going to go back here just for a moment. So if we wanted to generate a point for 20,000 CFM at about 12 inches, we would need to run this fan curve at a higher speed. So we can use the fan laws to calculate what that speed is. But here, we can actually see what that fan curve looks like. So we, on our previous screen, or on the original curve, our power peaks out at about 45 horsepower. We increase this fan curve is at 1,800 RPM, and the density in both of these curves is the same. So using the fan laws, we increase the speed from 1,500 to 1,800, which is about 20%. And down here, looking at the power fan law, our compressibility we're neglecting, our density is staying the same, and here we're just changing the speed from 1,800 to 1,500. 1,800 here is the new RPM, 1,500 RPM was our original RPM. That's about 20%, and we're going to cube that. So when you take 1.2 cubed, you get about 1.73, and that's 173% is what our new power values should be. And if you look up at the curve, we had that original value around 45 horsepower. And now if you multiply that 45 by 1.73, you get about 78 horsepower. And we look across here, and our peak value now is about 78 horsepower. And that's a 20% change in speed, but it almost doubled the power required. Small changes in speed can have a big effect for the increase in power. But these fan curves, you'll notice that the relative shape of the fan curves stays the same. And the points on those fan curves are at the same relative locations. So let's say you wanted to operate this fan, your original fan, at 600 degrees Fahrenheit. 600 degrees Fahrenheit is going to be a much higher temperature, so your air density is going to go down substantially. It's going to go at 600 degrees to 0.0375 pounds per cubic foot. The density term here would then change. 0.375 divided by 0.075 would be a density factor of 0.5. So our original power was at about 45 horsepower, and you can probably guess what our new power is going to be when I switch this curve. So here's that same curve, but if you weren't paying attention, you might think, oh, they didn't change at all. Well, they did change. This is our new curve here, and this is our original curve. So our original curve, we said, was at about 45, and because we used that 0.5 factor on our power, now our peak power is only at about 22.5 horsepower. That same factor is also used in the pressure, the density factor, and the term has reduced how much power, how much pressure we produce in the fan also has gone down by half. So you can see here, we reduced the pressure that we're developing by 50%. We also reduced the power that we're consuming by 50%. Our flow is not impacted by a change in density. So we're still getting the same flow values, and you can see how the points line up vertically through here, even though we changed the density. Energy is conserved. We took out how much pressure we're going to produce, and we took out how much power we consumed. So we can do both of those factors at the same time. We can change our RPM to 1800, and we can change our air density to 0.0375 and apply both of those at the same time. The peak power at 1500 was about 45. And what would you expect the peak power to be based on a change to 1800 RPM and a density of 0.0375? Well, you'd use that 173% increase for the speed before and a 50% increase for the density change. And now you put those two things together and you get a peak power that should calculate out at about 39%, or excuse me, at about 39 horsepower. And that's about, there's 40 horsepower would be a little bit higher than that. So it's coming in just as you would expect the fan laws, as the fan laws predict. Once again, the relative points for the curve of test are still at the same relative positions on the fan curve. So I've focused primarily on the power curve here because it's easy to determine that peak value. The same thing applies here to the pressure curve, only it's going up through a term squared. As I said before, the fan laws can be used to predict fan performance at other sizes. Those fans have to be dimensionally similar series. The blade styles and angles can't change through that. So you can't have a backward inclined wheel and then say, well, we're going to use this test and predict what it's going to do with an airfoil style wheel. it doesn't work that way. You have to use a backward inclined wheel in both of those, or a radial blade wheel, or whatever type of wheel you have. And I've spoken primarily about centrifugal fans. The fan laws also apply to axial style fans. And they apply even to a box fan that you might have cooling your house. The blade styles have to stay the same. The impellers and casings have to stay the same, but differ just only in size. And for AMCA certification, you can only increase the size of the fan. The fan laws can be used to reduce the size of the fan, but they're less predictable. Minor changes as you go down make a bigger difference. Also, as fan sizes increase, your Reynolds numbers lead you to get a little bit better performance as you increase the fan size. So minor changes for the blade gauges or other things are allowed in that proportionality of sizes. The manufacturers will use the fan laws to make those giant catalogs without testing every fan and every point. That's printed and PDF catalogs and electronic selection programs all are going to use the fan laws to produce the fan ratings. If you have an AMCA certified product, all those calculations have been confirmed by AMCA, spot checking all those catalogs before they are released.
Hey, Bill.
Yes, ma'am.
Could I ask you, at the bottom of the screen, there is a small banner that says AirMeet is sharing your screen. Could you either move that or try and hide it? Perfect. Thank you.
I thought that was only for me.
No, thank you very much.
So anyway, I mentioned that the fan laws could be used for other speeds, densities, and sizes. Here we have the term for size, which is the diameter of that fan wheel. And you could use any dimension, actually, just so long as you consistently use the same dimension. And for flow now, flow was proportional to speed, we saw. And now in the flow term, when you change size, it's going to be the cube of the flow of the diameter ratio. The second law for pressure has the diameter ratio in here. And in the diameter ratio, it's squared there. And then the power, this is where it really comes in. The power goes up as the fifth of the diameter ratio. So we can use those same fan laws once again to generate the performance curve at a new diameter. This is at the same speed and at the same density. And we went from 36 to 40 inches, which is about a 10% increase in size, but you can see we have a much bigger increase in flow and in power. And once again, we have those same, these are the full fan laws for diameter and RPM and density and compressibility. Separate fan law for flow, for pressure, and for power. So you can take those fan laws once again, and now we have a fan diameter increasing from 36 inches on our test size to 40 1/4, RPM increasing from 1500 to 1800, and the density decreasing from 0.075 to 0.0375. And the fan curve looks a lot different here, but it's still based on the same test data, and it's calculated per the fan laws. So in conclusion, the fan laws, fan performances ratings are developed by testing a fan in a laboratory using a test standard. Fan variables of flow, pressure, speed, and power are measured. The fan laws are used to normalize that test data to standard conditions. The fan laws are used to calculate new speeds, new air densities, and new sizes for fan performance ratings. AMCA certified ratings program confirms accurate performance test results so that everybody is getting the same results for testing their fan. And then the fan laws are used for the calculation of those fan performance ratings. And you get the same results from different labs, and they're calculated the same way, so you can compare apples and apples within the fan industry. There are some resources that are available in support of this presentation. One, you have the AMCA 99 Standards Handbook, which has all of the fan laws and how they are calculated, and in the same format as we saw here today. AMCA 210 is the laboratory methods of testing fans for certified aerodynamic performance. And then AMCA 201, and this is revision 2011 from 2002. This document is just about to be revised to a brand new version with full SI, IP units, and some additional data from testing with ISO and in Europe. So with that, I'm going to go, and I think I will come back here and I will stop sharing, and I will turn it back over.
Perfect. Thank you, Bill.
And we'll go live.
And I am actually, excuse me, I'm going to share my screen. And we've got a couple of little notes and such to go through. For everybody, please, if you have any questions, go ahead and type those into the Q&A option at the top of your right side panel. And let's go on presentation mode here. Just a couple notes for the audience. The recording and the PDF of this presentation will be available within 48 hours at the Odell website. If you have any questions, you can please follow up with Sarah about that. Actually, I'll show her email address at the bottom of this screen. It's sjohnson@odellassoc.com. For PDH credits, those will be issued within 15 to 30 days from today's broadcast. And please do remember that if you are seeking that PDH credit, you do need to fill out the survey. The survey will be or the link to the survey, I should say, will be in the thank you for attending email, which everybody will receive in approximately 1 hour. And the next program is Thursday, September 30th, the same time, 10 to 11 a.m. Eastern. The topic is fan law calculations. We'll get into a little more depth on the calculations with Bill. He will be our presenter for that program as well. So let's go to, I'm going to stop sharing for a moment so I can see the questions panel. And as I put in the chat box, if anybody has questions that are a little too involved or too lengthy to type, please go ahead and click the raise hand feature. That option should be at the bottom of your screen on the little control panel, and we can pull you on stage and basically unmute you so you can ask Bill your question live. So, Bill, I have a question for you.
Yes, ma'am.
Okay, the question I have is, if most fan ratings in catalogs are usually in table format, if we're looking at fan curves in this presentation, What's the difference? How do they correlate between the curve itself and the tables you see in catalogs?
Well, the point that you see in the catalog is actually 1 point from the fan curve. So we saw curves that covered the range from zero flow up through 20,000 CFM. Each point in the catalog will actually be 1 point from that curve, say at 15,000 CFM or 20,000 CFM or 5,000 CFM, and what the pressure required for that point was, what the pressure developed for that point was, the RPM required to operate at that point, and the power that that point would require from your motor.
Okay, thank you for clarifying that. And we do have, let's see, we have a question that has come in, and the question is, when would you not assume a ratio of 1 for K?
So when, with today's, most selection software today probably has compressibility built in, but it is an iterative process, and it does really complicate things. When your pressure is above 25 inches, you should very much consider using it. And if your pressures are above 50 inches of static pressure, you're really not doing anybody any favors by not including it. That pressure, compressibility actually reduces the amount of the size of the fan that is required to hit a specific flow and pressure point. It helps at those higher pressures. So it's good to have it in above 25 inches. It's almost necessary above 50 inches. AMCA recommends above 10 inches, you include it in the calculations.
Okay. Thank you, Stuart, for that question, and Bill for that answer. So does that tie into this question, Bill? When should fan law compressibility then be included in the calculations?
As I said, with AMCA, it should be included above 10 inches. And I'm not sure if they are checking that in catalogs yet. I don't think they are including that in the catalogs, but certainly anything above 25 inches, it should be included.
Okay. Thank you for clarifying that. We have a question from Tariq, and Tariq is asking, are fan affinity laws applicable to all types of fans, or are there certain exceptions?
As far as I know, they are applicable to all types of fans, and the fan laws of pump affinity laws really apply very uniformly throughout all fan applications that I've seen. There could be some spots where a fan goes through a certain transition point, and that's probably indicated by Reynolds numbers, where you would have an aerodynamic stall or some other function that would make the affinity laws a little bit less effective. But in general, everything that you're going to see, yes, they apply to all fan types, all fan systems.
Okay, great. So we have another question. Do you adapt the test tunnels for small fans over much larger units?
So that the fan test chambers have a range that they're available, they're suitable for use at. The large test setup that you saw pictured at AMCA is, I think, good to about 100,000 CFM. The small test chamber that you saw on the second page, the tubular one, is good to about 6,000 or 10,000 CFM, as I recall. There are limits within the test standards for how fast the air can move across the nozzle wall, and that is the main limitation for that type of test. The velocity across that nozzle wall. AMCA has test chambers that go down and can easily test at 100 CFM. So they have some very small test chambers also, and very large ones.
Interesting. Well, I'm saying interesting because I work for AMCA, so I do think it's interesting.
They
But
have a lot of chambers there.
yes, I'm not an objective voice in that. So I think, Bill, that's all the questions that we have received for today. Again, a reminder to everyone that the recording and the PDF version of today's presentation will be available within 48 hours on the Odell website. And we thank you all for attending this first session. We look forward to having you join us for the second and all of the sessions. And Bill, thank you for sharing your time and expertise today. I hope you enjoyed this as much as I know I did, and hopefully everyone else.
And thanks, Lisa, for having this, and thanks to Odell and Associates for hosting us, and thank you all for attending. I really appreciate it. Thanks very much.
Absolutely. Yes. And so we will see everybody in 2 weeks for fan calculations.
Thanks very much. Have a good
Thanks.
day.
Everybody have a good day.